wanted to start by something that's already been mentioned, but I think we don't understand the horror of Professor Fang's time in Fort Worth camp. So he says that along with mining coal, one of his jobs was to cart the corpses in a wheelbarrow to the morgue who had been killed in demonstrations. And at the same time, he read Wando and Lizhi's. How many have Wando and Lizhi elected by it? How many have read it? It's a very challenging text. It's the kind of thing that I used to keep on my shelf to say, hey, I'm not just an astronomer, I'm a physicist. So very tough reading. And so this is all very impressive. And we'll come back to this partway through my talk. So this is sort of the formal part of the talk. I'm going to first tell you how infrared astronomy came to the University of Arizona, and it connects with some of the things that Professor Fang did in terms of building groups. And then I'll give you a little taste of what is coming out of JWST. So infrared astronomy started 111 years ago when William Collins published some papers, a paper that he had used a vacuum thermocouple to take observations of more than 100 stars. And it happens that he was helped with the telescope by a graduate student, Seth Nicholson, who then finished his PhD and went to Mount Wilson. And Mount Wilson hired, in about that time, Edison Pettit, who was a very skilled instrumentalist. They used a detector like the one the Collins developed, but they also put down in the basement, this tells you how clever they were, a device where a galvanometer brought the signal down and shone a bit of light onto a photographic plate. And the photographic plate was driven with a screw so they could make what we would call strip chart recording of their signal. Of course, nobody here remembers what a strip chart recorder is, but you'll see in a second. This is their photometry. So they recorded the data, and you can see the quality of the data is shown by, this is one detector on the source, and then this is the other detector on the source. And those of us who remember single detector photometry, this is really excellent photometry. And their detector was quite sensitive. Hit the wrong button. And so and they published a couple of great papers. So this was all in 1920 to 1930, and after that, nothing happened. Elgin took a lead sulfide detector in 1951, and he did some infrared observations, and his paper ended with the stirring sentence that said, and really there's nothing to find in the infrared. Infrared astronomy finally started in the 1960s and 70s, and it really started at the University of Arizona, but there were, and this is important, Gary Nosevar, Martin Harwood, and I were at other universities. And why do you think okay. Why do you think it took 30 years for the field to actually take off? You know, we have been imbued with the idea that you make technical advances and then science takes advantage of that, and within 30 milliseconds, they're being applied in the field and great breakthroughs occur. So I gave a little summary of this to the Division of History, Astronomical History, and they were completely puzzled by this problem. And anybody solve the problem? Why did it take so long? Yes.
In space?
Pardon?
We had to get into space?
No. It's very simple when you think about it. It's because they were operating solo and nobody paid any attention to their work. And this makes me remember a little bit of Professor Fang. there were almost no citations to the work of Nicholson. And so they both went off into other fields. They gave up infrared astronomy. When you think about it, this emphasizes that science is actually a very social activity. And it's very, very difficult to go off completely on your own and do state-of-the-art science without the reward of colleagues, even more important, rivals. I mean, the most sincere flattery is somebody trying to do what you want to do better. And so this brings me back to Professor Fang. I think his reading on Lizhi was, given his circumstances, a kind of way to maintain virtual contact with his field. He was in total isolation, but he could sort of connect with other physicists in China that way. And then what struck me is that as soon as he came back to working academically, he established a group. And I found it really interesting at the end of that video, it was emphasized how much importance he put on working collegially and putting together groups and having people work together. And that's pretty much the story I'm telling you about infrared astronomy too. So when infrared astronomy got started, if you count up, there were 11 physicists doing it and 1 astronomer. Same thing happened in X-ray astronomy. There were 9 physicists and no astronomers at all. Radio astronomy was a little different. You had physicists and engineers, but almost no astronomers. And so that's a kind of interesting comment. And it turns out scientific initiatives are often powered by outsiders. And you can see from that statistic, and physicists are the most common type of outsiders. So physicists really provide a lot of the impetus to go off and do interesting new initiatives. There was one person that noticed Edith Nicholson's work, and that was Ard Kuiper. And in fact, he wrote this paper in 1938 using their infrared data on stars to develop, whoops, it went back. There we are. To learn how to correct the photometry of stars to their total luminosities. And that's important because Kuiper came to the University of Arizona, and in 1965, construction was started on the Lunar and Planetary Lab. And Kuiper had a somewhat free life academically because there was an astronomy department across the street, and it was their job to teach astronomy courses and have a balanced faculty that had all different kinds of astronomy represented. And so Kuiper did something totally different. Yes, he hired some planetary people, but he also went off and hired really accomplished scientists in a couple other fields that he could build real expertise. And he already had an interest in infrared astronomy, so that was one. He had Tom Garrels, Stuart Coyne, Kostakowski form a colorimetry department. And this was beautifully summarized by Harold Johnson, who was one of the people Kuiper hired right away. He declared, I am the stellar photometry department of the Lunar and Planetary Laboratory. And Harold really was. And there we are. Whoops. So these are the infrared astronomers that form the infrared astronomy department of the Lunar and Planetary Lab. There was Harold at the lower left. Frank Lowe was posted out here by NRAO to be the telescope scientist for the millimeter wave telescope that still on at peak. But that was not technically ready to go at all. It was kind of a technical disaster. And so Frank quickly joined Harold at the Lunar and Planetary Lab. And then it was Kuiper. However, the problem was these were three immense eagles. Each eagle would pretty much fill the building of the Lunar and Planetary Lab. And there was too many eagles in one building. So Johnson stormed out in 1969. Nonetheless, we had the start. But there's a problem. all the measurements made at the Lunar Planetary Lab were using ground-based telescopes, assisting 1-inch capable for planetary photography, and then the roll-off shed telescopes, the lunar telescopes that Jose had built for his photometric effort. And the problem is doing particularly thermal infrared, say 10 microns from the ground, is like detecting a gnat in a blast furnace. So the problem with that is the telescope is warm, it goes in the infrared. Worse than that, the atmosphere goes in the infrared, and it doesn't even sit still. The wind is blowing warm cells over the mouth of the telescope. And so although using the telescopes was great, a lot of progress was made, we really want to do something different. And so if you go to space, the background in space is 10 million times lower than it is for the same size telescope on the ground. And so there was a series of space-form cooled infrared telescopes, of which the one that this sketch is of is Spitzer. And in a low point in the Spitzer mission, Frank Lowe had this idea that, hey, we could cool this telescope by radiating its heat off into space, and then we only need a little bit of liquid helium to cool the instruments. And this is Frank's sketch, which grew into the concept for the Spitzer mission. So remember, the concept is don't carry a lot of coolant, don't carry a trial cooler, but space cool your telescope and then have a dedicated cooler just for the instruments. And if you go to space, there's the match. The blast furnace is gone, so there's a tremendous gain. But lots of other things happen. Infrared detector arrays. Oop. Okay. Infrared detector arrays were developed at about the same time, and this is a little demonstration of how important they are. This is the first real map of the center of our galaxy. It's made with a 200-inch telescope. It took 3 nights. It was a single detector, and the detector field of view is this aperture. And it was scanned across along the dashed lines. You'll notice that the contours go where there are no dashed lines. So, Hopper and Beckman made up the contours where this wasn't time to get the data. The center image is a 2-mass sky survey image with 256 by 256 detector arrays that were developed in the Nikos space camera. That took 8 seconds. And the image on your right was using a 1,000 by 1,000 infrared array. And it's not scientifically very useful because there are so many stars, it's what we call confusion limited, and you can't get any information out of one star reliably. And with modern detectors, that image would take a minute or two. So you can see a tremendous gain with the infrared detector arrays. And there's another issue, which is if you want to do really distant cosmology, obviously in high redshift, the absorption in the intervening material basically removes your view to view any really high redshift objects. And so this is a spectrum that is shifted to a redshift of 6. And you can see the Lyman alpha is where the standard ultraviolet visible spectrum starts to come in. And there's basically no information that you can get at standard visible wavelengths over at 6,000 or extras or shorter. And there was sort of a social problem, which is 25 years ago, cosmological astronomers really thought that the infrared was the realm of beasts and dragons. They had no idea that you could do any real cosmological astronomy in the infrared. And in fact, a breakthrough was made by Ishigami in the office right next to mine in our group when they discovered a lens galaxy in a redshift of 7 using Spitzer data. And nobody before could believe that an 85 centimeter telescope could reach to redshift of 7. And that was kind of a revolution in thinking. And so all those things came together. the science, the fact that you need to go to the infrared cosmology, you have sensitive infrared rays, and you have to go to space and have the whole telescope, and that resulted in the James Webb Space Telescope. And we had a lot of involvement in the James Webb Space Telescope. So here are Marcia and I, as close as we were ever allowed to get to the telescope. Well, that's the real telescope. It's in the clean room at Northrop Grumman. And so Marcia was the principal investigator on the near-infrared camera. I was the co-principal investigator on the mid-infrared instrument. So, as you said, it was sort of a family affair rather than just a university affair. In fact, it was sort of amusing. I wrote a proposal to work on the mid-infrared instrument rather quickly with the idea that we worked tremendously hard on the near-cam proposal. Well, they'll probably turn it down, but at least we can get a little bit involved. We had this other instrument. And Marcia came down the hall and said, "We won." And then my telephone went off, and I was told that I won too. So there we were. So we had 20 years of a topic to talk about over dinner. Okay. Now I want to talk about some JWST. I put discoveries up here, but I decided that's not right. It's too early. Well, JWST has been a success because it's shown us a lot of things we don't understand. Think how disappointing it would be if we went up there and after the first year, we said, okay, we understand everything we've gotten out of this mission, let's go build something else. And so I'm going to talk about things that, unlike a normal colloquium, I'm not going to tell you when the answer is at the end. You're going to be left with, and you sort of do a lot more work at the end. And so I talk about two things. Galaxies and heavy elements form too early for what we thought before. And well, supermassive black holes, there's so many new things there that we didn't anticipate that we're just really confused. Okay, the first surprise, and this made the news, so probably all of you are somewhat aware of it, there were two galaxies that were too bright. Or if you use the standard conversion of brightness to mass, there are too many massive galaxies very early in the universe. Well, that isn't so hard to fix. You have to make some adjustments in your theory of galaxy formation and what kind of stars and so on you have in them. But the next one is much worse. And many of these things were worked on by young people with connections to our infrared group. And so I show pictures. This one is a real puzzler. This is a galaxy at a redshift of 14.2. That puts it 300 million years after the Big Bang. And this very bright line is oxygen. Well, oxygen is not supposed to be around 300 million years after the Big Bang. And so it was supposed to require lots of generations of stars to get heavy elements like that. And in fact, here's a little primer on that. It was thought in the 1940s that you could get the heavy elements out of the Big Bang, but that turned out not to work because you couldn't get past elements with 5 and 8 nucleons in them. And so then it was turned that stars could do this. And the key was you could get past those elements with stars if you use a process in a saltpeter found where you take 3 alpha particles and merge them into carbon. So you get to 12 nucleons without dwelling too long at 5 or 8. And so this has been the standard theory of star formation. But what kind of stars do we have at redshift of 14.2? We actually now know that the galaxies have 10% as many heavy elements as we have in the sun. And the normal process, meaning what we see in our neighborhood, says you can't have stars heavier than about 100 times the mass of the sun. And the reason for that is if they have too many metals, they blow themselves apart when you get more massive than that. And so that just doesn't give you time to produce these heavy elements at 200 million years after the Big Bang. But if you can make stars up to 200 or 300 solar masses, you can get around this because they evolve quickly. And you can do this if you have very few metals in their atmosphere, so they can get through this 100 solar mass barrier before they get blown apart by the pressure of the photons on materials in their atmosphere. So that's a possibility. It's one that most astronomers hate. They do not like the idea that what we call the initial mass function, the range of stellar masses go up and be really different from what it is locally, but I think they'll get over that. It's very hard in astronomy to rid yourself of being led to what happens locally that's very well studied. But there are other suggestions, but that's a way to solve that problem, we hope. Okay, next problem. Which came first, the galaxy or the black hole? And here's just that. Okay. So prior to JWST, almost everyone thought that the way you got black holes is first you form massive galaxies, and then you form black holes within the galaxies, and by dynamical friction, that is where the black hole basically causes stars to get scattered out of its way and it spirals into the center. The black holes are centered in the center, they converge into a bigger black hole, and then when galaxies collide with each other, their black holes are centered in the center of the merged galaxy, and you can gradually build up black holes. And so when I say a black hole, what I'm really going to be talking about, because the popular thing is how can you see a black hole? It's an active galactic nucleus. There's a black hole in its center, and then it has an accretion disk around it where very hot material is orbiting. And then outside of that, it has a dusty torus, which is the inner edge of which is determined by the sublimation of the dust in that torus. So remember that. We'll come back to that. So, let me get to the right here. Here we go. So this is an optic lesson. This was a paper that was published 17 years ago. And it has such a beautiful figure explaining this theory of black hole and active galactic nucleus evolution, but people still use it. It's all wrong, and we even knew it was wrong before JWST was wrong. It's such a seductive picture. So what happens is you have a normal galaxy. It's sort of in a cluster. The galaxies merge. Material falls into the center. The black holes merge. The material that falls into the center goes into an accretion disk. You form a quasar with a merged black hole, and you end up with a dead elliptical with a big black hole in the center. And that just exemplifies the idea of the galaxy formed first, and then the black holes form inside the galaxy. And a consequence of that kind of model is that the dispersion, velocity dispersion, is a measure of the mass. This is the black hole mass. This is the mass of the galaxy. And there's a nice proportionality between black hole mass and the mass of the galaxy over all the nearby galaxies that people have studied this in. Or we can use as a surrogate for the dispersion, the 2-micron brightness of the galaxy, and the relation is almost as good. So the 2-micron brightness of the galaxy kind of tells us its mass. But we can test this relation. But first we have to know how to measure the black hole mass. And the way we do that is, remember the picture I showed you, the active nucleus. Inside the circumnuclear torus, you have clouds of gas, and they're orbiting very fast with Keplerian velocities. And when they make emission lines, the emission lines are broad just because of the Doppler effect of the very high orbit. So if you take a spectrum of these galaxies, you have these broad planes on the emission lines, even though it's a hit black hole masses. And I just told you we can use the 2-micron brightness or more sophisticated, use a number of infrared bands to get the galaxy mass. And here's what you get. This is the ratio of the black hole to the galaxy mass as a function of the redshift. And everything looks good out to a redshift of 4. The ratio is pretty constant, like we saw locally, but doesn't look so good out here at redshift of 4 to 7. And that's going the wrong direction. If the galaxies come first, and then the black hole, you would expect these points to be below the line. The galaxies would be more massive than the black hole, and instead, it goes the other way. And we can look at this in another way. This is a plot of the galaxy mass, stars in the galaxy, and the black hole mass, for a whole bunch of different kinds of objects. And so the sort of local relation, and the width here is to indicate the scatter on that relation. It's not a really precise relation, but it sort of runs here. The most massive high redshift objects are up here, and they're not too far off that. And I'm showing this run on complex simulation that shows, in fact, their deviation in general is probably selection effects, that we can't see a complete sample of the might be found. But what happens down here when we get the low mass galaxies, and still pretty massive black holes, and there's a huge overmassive black hole problem, and that's one of the major things that they have is yielded about black holes and their galaxies. So it kind of reverses the whole thing of which came first. It's like maybe the black hole came first of the galaxy, how it had to figure out how to flow around it. And so there's a lot of variation. And so we obtain images of what used to be the highest known redshift quasar, and we were able to show by a number of different ways that its black hole is a 3 times 10 to the 9 solar mass, and so that's a really massive black hole. Excuse me, the quasar black hole is about 1 times 10 to the 9, and the galaxy is only about 3 times 10 to the 9, so that's way off the local relation. And so by imaging in a narrowband filter that isolated that oxygen emission line, we were able to find all the galaxies around this quasar. And the problem is, if all those galaxies merged in the quasar host galaxy, you still could not get to the standard relation. In fact, this shows the quasar field here, and the adjacent field, because there's the adjacent fields to do, we've got the quasar field and the adjacent field together, and they're virtually identical in the number of galaxies per arc minute. And so even if all the galaxies close to the quasar merge with this host galaxy, it'd be off the relation. And so this is where we are. If the black hole didn't grow at all from T of 7 to locally, you still would not come down to the local relation of the galaxy to the undermassive. And so this raises the question of whether they're naked supermassive black holes floating around in space. And I think we have almost no way of detecting them. But wait, there is a possibility. We used to think this was science fiction. I don't know if anybody here has watched Star Trek. Yes. So the most exciting episodes were when the Enterprise started to fall into a previously unknown black hole. And they were desperately in the ship shook around, not out of control. I think they took the camera, but anyway. But that's what we're finding. We're finding some evidence that you do have very massive black holes that are out there and maybe are not advertising their presence. Okay. The problem with this very massive black hole, and no way to grow it with galaxies, either as host galaxy or surrounding galaxies, is there isn't time to form it by the standard way. And so the way you have to start it is to have some sort of process that's called direct collapse, where all the mass in the black hole falls in and forms a black hole without any intermediary, any particularly long time. And maybe you start with a black hole that's, I don't know, 10 to the 6 or something like that, solar masses, and then you can grow it up to 10 to the 9. But you can't start with like a stellar mass black hole and get there. And this is a very popular subject. There's about one paper a week that comes out on this subject. So I'm not going to pretend to be up to date on this result. So instead, I'll move to something else that bears on this. So this is a spectrum of what I think everybody has heard of now, little red dots. This is a form of very compact object that was not known until JWST came along. And its characteristic, it was found not by taking spectrum, by looking at photometry, just colors, but its characteristic is a very blue spectrum, flat spectrum over here, in the violet and the blue, and then a very red spectrum going out into the infrared. And Pablo Perez Gonzalez generated the spectrum here by adding up, people from taking spectra of these as time goes on without figuring out what to do with them. We added up 211 spectra. And then he also took infrared photography from Miri, the spectra from the near spec instrument on JWST. So you can kind of see how this looks. It has some standard emission lines, and it has this characteristic continuum. And let's see, we get to the next one. Okay. So initially it was thought, and the reason they were dots was the people who did not have any host galaxies. And that's because initially their images were taken with the long wavelengths in NIRCam. So these are two sample images. But, oops. Pierre Rinaldi in our group has the idea that if we look at the short wavelengths of NIRCam, the resolution is much better. If you go to 1 micron, the diffraction limit is 4 times better, and miraculously, JWST almost delivers the diffraction limit at 1 micron. And now you can see that they have host galaxies. Now we can go back to that plot. Maybe we can go back to the plot. So the open circles are little red dots where the central mass is being determined by the line width, which I just explained to you. And what Pablo did was from that spectrum where he added up all the spectra to get a very high similarized average spectrum, there's a line ratio, magnesium to iron lines, that's been shown to estimate the Eddington ratio of the black hole. That is, how close it is to the Eddington limit. And so you can use that and the luminosity of the source to estimate the black hole mass. And what is shocking is Pablo's points come out here, and all the points with line widths come up here. So there's something wrong, and it may be that the line widths in these sources are not telling us about blurring motion about black holes, they're telling us about turbulence or something that's not related. So this just says we don't even know what the black hole masses might be in these objects. I warned you about stop and explain things. I was going to leave problems. So one hypothesis that kind of makes sense to these things is that it might be, remember we want to have a mechanism for direct collapse. It might be that have been done quasi-stars. You can have a really massive body of gas that has a black hole in its center. It might be 10 to the 6 solar masses. And that this will eventually grow into one of these direct collapse black holes. And so that's what a lot of the excitement is with all those papers that are coming out. Is can we explain this? Because these are the kind of the predecessors of the local galaxies with standard black holes in their center, because they're growing them from quasi-stars. But it's very hard to tell because It's very basically dust all around the center of these objects, or perhaps very dense gas, we don't know which, but you can't actually see what's going on inside. But it may be the LRDs, since we don't know very many of them that are close, and that's a real problem. We can't make a black hole disappear from the universe, so they have to evolve into something. And maybe they're forming these direct collapse black holes, and they are now what we would call standard active galactic nuclei galaxies. We'll see. I make it sound very definite, but don't trust me. There's a lot of active work going on this. Okay. So, a summary. So first, I wanted you to get a flavor of the evidence in science as a communal activity. And I thought that was particularly appropriate because Professor Fang clearly had a very strong appreciation of that, and that's basically how we work. In that you should thank your rivals for being so aggressive in attacking your work, because that shows they really appreciate it. Just remember that. That will be needed in some dark times. New initiatives are often led by outsiders. The people in the field are too busy doing the standard things, and it really takes somebody without a perspective on the field and introduce a new perspective. And this is the physics part I want to emphasize. Outsiders are usually physicists. And there's no to have the first infrared astronomy community, and that grew because John Kuiper was basically an infrared astronomer. He built a lab here where he could pick whoever he wanted to hire and didn't have to have a balanced faculty. And he hired leading infrared astronomers, and so we've had 6 decades of leadership in the field. The second part, I wanted you to realize that JWST has left us unfounded. And that's good, right? It's produced a lot of surprises, and somewhere in there are answers. Now, we believe the mission may continue to operate for another 15 years, so we hopefully have time to solve some of these mysteries. But right now, I would say the community is at a stirring around with lots of ideas and not a well-determined solution to the problems I discussed with you. And so these are the things I mentioned that are going to be the subject of a lot of research over the next 5 to 10 years. How galaxies could form so early as the universe and how they could produce heavy elements that early. The first galaxies we can find and spectra that look like they're local galaxies in terms of oxygen lines and so on. And that is not supposed to be the way the universe behaves, but the universe is telling us that that's how it does behave. And the supermassive black holes have provided us with so many problems. I think they will keep these students working for years trying to figure out what's going on there. So thank you, and I think this is a real tribute to Professor Fang. I'm really happy to give the sort of kickoff lecture at this series in honor of him.
Oh, it's okay. Hello. Here in Italy, it's 1:00 at night. I was very interested in your talk. Can you make sure, please, to send to all the participants or to put your slides in available?
Yes,
Your talk is very important to us. We are working exactly on this topic, how the red dots could be.
Okay, I will try to do that. I think Fang will.
Yes, I will make sure it's
Not
available.
away until I look at the slides.
Yeah, the whole event is being recorded, except the movie part, and then the link will also be available for those of you who cannot, for those of people who cannot join us. But for the moment, any questions for George from outsiders and insiders?
You see, if I presented solutions, they want me to clarify them.
Thanks, George, for the very, very talk.
Question on direct collapse. I know you don't know, but the theory of a direct collapse is a massive molecular cloud or a massive gas cloud that collapses to its black hole without undergoing star formation. Is that because maybe the cloud is too
You want me to answer? I said I wasn't. Okay, let's go into a little more depth on this. Normally, those very red spectral energy distributions in the little red dots would be ascribed to dust, but they're a little too hot for dust. So another theory that makes a lot of sense is just because it's got very dense gas, and so the gas is sort of optically thick. And under those conditions, with all the energy that's coming out, I do not believe that the gas would necessarily break up into stars. You have to have turbulence, some sort of disordered system. And so I think it's more complicated than that.
so they're essentially quiet gas clouds that then can't form starvation because of
Well, you have to think out the local box, out of the local box, right? I mean, these are gas clouds that are almost anything we've seen locally. They're deeply massive, they're very hot, and they're very compact. And so this is the problem with trying to figure these things out, that our local experience is not a very good guide for getting a model for what's going on. But as I said, with the astronomers and stars and up to 200 or 300 solar masses, it's hard to get astronomers to get out of a local mode of thinking. And so you sort of have a burden of proof, and you say, must be freaking solar mass star. Astronomers will say, can't exist. So they probably do exist.
Okay, one more question.
Thanks, George. That's a very interesting talk. I have one minor correction here. LPL was actually founded in 1960.
I gave one the building started.
Okay, yeah, but it was LPL was housed actually in this building.
Yeah. Bill should know, he was director for quite some time. And I should mention a coincidence. When infrared astronomy started at LPL, Professor Fang was in forced labor, and he got out of it in 1972, and that's when infrared astronomy was really starting to take off. And much of the taking off was happening in the planetary lab. And Bill was in charge of the latter part of that, although he went for just how more away from it, and Bill was the director.
Any other corrections from consumers?
He was baking bricks in forced labor, so a lot of infrared.
I'm not quite sure what he was doing, but what he was doing, but a bit about carting the dead bodies off to the morgue in the wheelbarrow got my expense.
I know he was baking bread. He was making bread,
Yeah.
not bread.
Bricks, yeah, bricks.
Bricks,
Yeah, and
bricks.
there was a picture of it in the movie. These
Bricks.
kilns firing bricks by the ancient Chinese method.
Lots of humor. Okay.
Well, but there were two things. There was working in the mine, and then there was making bricks.
Yes.
According to what I've read.
Yeah.
And
All right, babe.
it must have been really miserable. I mean, I can't imagine working all day at the brick kiln or working all day in the mine and then saying, I know. What a wonderful book to relax with. That's what amused me about those two things.
Let me thank all the speakers for today's event, and thank you all for coming. I also want to thank Kyle for providing all the IT support, and also Katie for arranging the whole thing, including the receptions. And now go out and enjoy the reception and the books. Thank you very much.
Very nice.
Yeah.
white things. They're really